Hi and welcome to this Leaving Cert Higher Level Applied Maths video. In this video, we're going to look at a previous exam question. This question is from the 2024 Higher Level paper and it's question 4. A snowboarder of mass m is traveling with the velocity v1 when he enters circular arc AB at point A. And we can see that in the diagram on the right. AB has radius 6.7 meters and center C. A, B, and C lie in a vertical plane, and AC is vertical, BC is horizontal. A student models the motion of the snowboarder, ignoring the effects of friction and air resistance. So part 1 asks us to draw a diagram to show the forces acting on the snowboarder when he is at point D, where CD makes an angle of alpha with the downward vertical. So just focus on what we're told. So D is here along the arc. So we'll start with our snowboarder, and weight is always a great force to put in first. We always know it works straight down, so our weight is equal to mass times gravity. The only other force acting on the snowboarder is their reaction, since the snowboarder is on the ground. The ground is curved. However, the reaction is always perpendicular to the ground, so it's going to come out like this. So here is my reaction, which we're going to call R. Remember that we were told that this is a circular arc, which means we have centripetal acceleration towards the center. So that is our acceleration there. And just to think about that angle, we'll need it for resolving. We don't need to resolve to get our marks for just the force diagram. What we have here is absolutely sufficient, but just for ourselves, it's handy to know that we can add in the angle here against the vertical. Be so careful. Really think about it in terms of the bigger diagram, if that helps. If we put a vertical line there, we have that lovely Z shape of alternate angles, and there is my alpha. So just pay really close attention to where that angle is going in, especially when we're dealing with circular motion, because often it's not in the most obvious place. So part 2 then says express the reaction force of the snowboarder at point D in terms of M, V1, and alpha. So what we're dealing with here is vertical circular motion. And what's really nice about vertical circular motion questions, although they can be quite challenging, we always approach them the exact same way. So this is just an extract from the revision booklet, which goes through how we work with our vertical circular motion questions. The first thing we want to do is we resolve weight. Always weight, because if we're dealing with like a reaction or a tension, they will be in the direction of the centripetal acceleration, which means the thing that's in the wrong direction, the thing that is not currently parallel or perpendicular to our acceleration or our movement, is going to be our weight. So we always resolve our weights into two parts. We want to think about it either towards or away from the center of the circle and tangential to the circle. It really just depends on the question, whether it's towards or away. So step 1, we're resolving weight. Step 2, then we use the conservation of energy. That gives us our first equation. And then step 3 is we use F equals ma. That's going to be thinking of A in terms of our centripetal acceleration. So we have or omega squared or v squared over or. Either of those will work. That gives us our second equation. And our final step then is to solve that. So even though this question seems a little bit tricky, we're still being asked a vertical circular motion question, and we're going to follow these steps. So now we're going to follow those 3 steps. So basically, step 1, we're going to resolve weight. Step 2, we're going to use the conservation of energy. Step 3, we're going to use F equals ma. So what we're going to do, we're going to take our force diagram that's there on the right that we had in the last part, and we're going to resolve weight. And that's so important. And a really common mistake students make is they resolve our reaction. So really focus on the direction. And it's so important when you're doing a force diagram to put in that direction, which is in red there with our A. And that's where we want all our vectors to either be parallel or perpendicular to A. So W is the one we need to resolve. So here's our force, and firstly we have weight. So this is mg acting straight down. We then have our reaction force, which is up here, and we have our acceleration pointing inwards. So we want to resolve our weight, our mg. So what we're going to do, we're going to draw in parallel and perpendicular vectors to mg, and I'm going to put in our angle to the vertical. And if you want to go back to your original diagram and think about, let me put it in a different color. So we're going to resolve weight here and here. And if you figure with the alpha, we have vertically opposite angles. That's where our alpha is going. So use your original diagram to help you figure out where the angle is going. That means we have here mg cos alpha, and this side is mg sine alpha. So the adjacent side is always cos, the opposite side is always sine. So we end up with our resolved vector is looking like this. We have mg in a different color, which will suffice for the exam as seeing it as not double counted. However, if you want, you can take that out. So just make sure it's distinguished, or what you can do is you can like put a line through it to show that you've already dealt with it. But like I said, different color should be absolutely fine. So step 1, done. We've resolved our weight. Step 2, so this is equation 1. So we have the conservation of energy. So the energy that's potential plus the energy that's kinetic at the start should be equal to the potential plus the kinetic at the end. So we're talking about D, and we're going to start at A. So these are our these are 2 points, A and D. So we want the first part, we're talking about at point A, and here we want at point D. So potential energy at A, so that's mgh. There is no height, it's at the lowest it can go, so we're going to put in a 0 for that. And that is equal to, that is plus kinetic energy at half v, and the velocity is v1, and that's squared. So then we have the potential at D. Now we need to think about, well, how high is this? So we have a few different ways we can think about it. So the total height here is 6.7. So the length from A to C is 6.7. And we can work out this little part of the triangle because we have our alpha. So this here is 6.7 cos alpha. So we can write that in terms of alpha, which is what we want. So we can say this piece here is the 6.7 take away 6.7 cos alpha. So that gives us mg, and our height 6.7 minus 6.7 cos alpha plus kinetic energy a half. We want this in terms of our velocity, v1, but it doesn't mention anything about the velocity here, so I'm just going to use this as v2, so our velocity, and that's squared. So we can get rid of this. Everything else has an m, and we can get rid of the half as well. So we get v1 squared is equal to 2g 6.7 minus 6.7 cos alpha plus v2 squared. So v2 is at D. So not a lot I can do with that at the moment. So we go to the second equation. So that's my conservation of energy. And then I do F equals ma. Remember, we're always looking at the direction of motion. The direction is given in our diagram. Really good habit to put that in anytime you're doing a force diagram. So what is pulling it to or with that direction? That's going to be or. Pulling it against is the mg cos alpha, and that is m times a. Now we have 2 different options for our acceleration because it's an centripetal acceleration. We have v squared over or omega, or omega squared, or, so either or. Think about the question. We have nothing about omega or our angular velocity here, so that's not going to be the one we're going to use. We're going to use v squared over r. So that's v squared. Now our v is the velocity at point D, because that's where we're doing the forces for. So that is v2 squared all over our radius, or we know our radius is 6.7, so if you want to put that in straight away, that's absolutely fine. So there are two equations. So we want to have the reactionary force, which we do, in terms of m, which we have v1 and alpha. The problem at the moment is the velocity 2, that v2. They didn't ask us for that, and they don't want that in there. So that's why we're going to use our two equations. We're going to isolate our v2 in equation 1, and then sub that into equation 2, and figure and isolate our or to get exactly what we want. So just clearing the screen to give us a little bit more space. So I'm actually going to leave the square here because we're gonna need that when we sub it back in. So this becomes v1 squared minus 2g 6.7 minus 6.7 cos alpha. Plugging that in, we get or equals. I'm going to bring this across, so I get mg cos alpha plus m times all of this, so v1 squared minus 2g 6.7 minus 6.7 cos alpha all over 6.7. So this is effectively our answer, but we just want to do a little bit of cleanup on it. So we're going to leave that first piece as it is, cos alpha, and I'm going to break up the second fraction. So I get mv1 squared over 6.7 minus 2mg all over 6.7, 6.7 minus 6.7 cos alpha. Now we can see in the second fraction that tidies up a little bit for us. So we end up with mg cos alpha plus mv1 squared over 6.7. And this multiplies out to give me 2mg times 1, which is 2mg, and then minus by a minus plus 2mg cos alpha. You can multiply out those 6.7s and then divide in that 6.7 from the denominator, whatever way works best for you. Our reaction then is 3mg cos alpha minus 2mg plus mv1 squared over 6.7. Cleanup is not hugely important here. It's just nice to bring together those mg cos alphas because they do tidy up nicely. So we're then told that the snowboarder reaches point B with vertical velocity v2. So we're at this point here, and we have vertical velocity, so straight up, and that's going to be v2. So we had horizontal velocity there at the bottom and vertical velocity here at B. So we're trying to express v2 in terms of v1. So we're going to use the conservation of energy, similar to what we did in the last part, but we're using different points. So when we have the energy at A, so at A, we have potential plus kinetic, and that should equal the potential plus the kinetic at point B. So here we have the potential at A is going to be mg, and there is no height. It's at as the lowest point it can have. And then we have a half v1 squared. We have the potential at B, which is mg, and the height is going to be 6.7. It's just that vertical height, plus a half and v2 squared. Now, don't be worried too much about that idea of horizontal versus vertical velocity. How do we deal with that? When we deal with energy, energy is a scalar, which means direction doesn't matter. So when we talk about half mv squared, that v actually stands for speed. So all we put in is the actual magnitude. We don't care about like the direction, the sign, or anything like that. So it is absolutely fine to put in exactly as we have here. So it's really, really important to understand the difference between vectors and scalars, the impact it has with regards using formula. And it's really important to understand when energy, for example, is scalar, work is scalar versus velocity being vector. It's really important to know that. So this goes to 0. We have the m's disappearing. We want to write v2 in terms of v1. So we're going to multiply across by 2. So we got v1 squared minus 6.7 g is equal to, sorry, I've lost my 2 there. So it should be minus 2g times 6.7. We'll multiply that out in a sec. And we have v2 squared. So v2 is going to be the square root of, we have v1 squared minus 13.4 gravity. Or if you want to put that in as 9.8, that's absolutely fine. At point B, the snowboarder leaves the arc and moves vertically upwards through the air. The student wishes to calculate v, the velocity of the snowboarder, t seconds after he leaves the arc. The force due to air resistance is now modelled as mkv. Part 4 asks us to draw a diagram to show the forces acting on the snowboarder while he's moving upwards through the air. So here is our snowboarder. And the first thing we're going to put in is weight. And we know how that acts and we know how that works. So that is mass times gravity. Now, for air resistance, we need to think about how he is moving. So he is moving upwards, which means the drag or that air resistance is going to work in the opposite direction. So that is mkv working down. There is absolutely nothing pushing him up. He does have an initial velocity. That's why he's moving up, but he will be decelerating that whole time. So then part 5 asks us to show that while the snowboarder is moving upwards through the air, so this scenario we've just drawn out, the rate of change of v with respect to t can be expressed by the differential equation dv dt is equal to minus g plus kv. Now, we know anytime we have a force diagram, we are working with F equals ma. So our force will always go in the direction that we are moving. So there's nothing pushing us in that movement direction, meaning we have a minus weight and a minus air resistance, and that is equal to ma. The mass it can be divided across, and we're left with acceleration is equal to minus, I can pull that out in front, g plus kv. And then the only thing we've left to do is replace our acceleration with the rate of change of velocity. So that gives us dv dt, which is another way to say a, is minus g plus kv. So part 6 then says solve the differential equation to find an expression for v in terms of t, k, and v1. That's really, really important. That v1, it's so important. It is a little tricky part that was thrown in and was easily missed. So we're talking about the snowboarder moving through the air. It went into the air with the velocity that it had at point B. And it's important to remember that at point B, the initial velocity was actually v2. So I'm going to just make a little note of this. So easy to miss in an exam. So velocity at B was v2. So that's our initial velocity. A lot of students went straight to putting in v1 because that's what it asked for. However, in part 3, we were able to write v2 in terms of v1, and we're going to use that fact, but it's important that we really think in terms of our limits, that we have an initial velocity at point B. That's where it starts moving through the air. That is v2. So we have dv over dt is equal to minus g plus kv. This is something we've actually seen in a few questions. And we are going to leave the minus on the right hand side and bring everything else across. Remember, when you're separating these out, you really want to focus on division and multiplication. We should never have any adding or subtracting. And the reason for that is it needs to be multiplied by that dv or that dt. If it's added to it, it makes no sense. It cannot be integrated. So when the time is 0, our velocity is v2. And that's really, really important. That's what we're looking for. So then we have time and velocity v. So the right-hand side, very straightforward, minus t, and we're evaluating that between 0 and t. The right-hand side is something in the form of a plus bx, which is just a version of 1 over x. Remember, if we have 1 over x, it's going to integrate to ln x. If we have something a little bit more complicated, remember the ways to look out for this, there's always be a constant on top. It doesn't have to be 1, and it'll always be a little linear function underneath, so it'll be to the power of 1. In this case, it'll be a v to the power of 1, which is what we have. This is ln a plus bx, but because it is a version of the chain rule going backwards, we have to divide by the derivative of the inner function. So we're going to divide that by b, which means this left-hand side becomes 1 over k ln g plus kb. You can write that as a full fraction, or you can pull that out in front like we have, whichever way works. Okay, so now what we have is we have 1 over k natural log g plus kv minus 1 over k natural log g plus kv2 equals minus t minus a minus 0, which is just going to be 0. Now, focus on what we want. We want to find an expression for v. So just v, not v2 or v1. We'll plug that in a minute, but we want to get v on its own. So first thing I'm going to do is I'm going to pull out that 1 over k in front, and then I'm going to use my laws of logs to bring these two together. I get g plus kv all over g plus kv2, and that's equal to minus t. I'm then going to bring that k over, g plus kv over g plus kv2 equals minus kt. Now, just a bit more space to finish this off. We're going to get rid of that natural log. Let's do e to the power on both sides. And we get g plus kv over g plus kv2 is equal to e minus kt. Let's bring over that bottom line. So that's g plus kv2 e to the power of minus kt. kv is equal to g plus kv2 e to the power of minus kt. Take away that g, and final step is then we're dividing by k. And we're nearly finished. So all we need to do now is answer the question, which is asking us for this in terms of not v2, but instead v1. So we're going to plug in what we have here. So that's g plus k times square root of v1 squared minus 13.4 g e to the power of minus kt minus g all over k. And given its velocity, that is meters per second.